Hello all. In the last video, we discussed the definition of digital twin. In this session, I'm exploring the components of digital twin. I've taken some time to learn and reflect on this topic, and I'll illustrate it with an example to simplify the concept. I have referred Mr. Martin's System Lifecycle Management book to study these concepts. Thank you, Mr. Martin and team. Thought a smart washing machine would be a better product to illustrate digital twin components. Here I have listed usual life cycle stages as designed, as built, as maintained, the phases, and all the engineering systems, most of the key OEMs. And from the beginning, I wanted to take the components as differentiate the real world components and then the virtual world components, system-based ones. And the IoT platform, Internet of Things platform, enterprise-based one, where the most of the elements of digital twins are located in the enterprise IoT platform. Let's move on with the digital twin core. Digital twin core is a variance-free one, which consists of various submodel of digital twins, like the subproducts or the local modules. The major difference between the digital twin core and the digital model, the digital twin is a variance-free one, because like in the 150% BOM digital model one, it is designed for multiple configurations. For example, here the 4.5 cubic feet and the 5 cubic feet drum consists in the same product model. But like when we work with the digital twin core, we expect to have an 100%. So that's when the physical twin comes as expected. So once this has been matured, I mean the engineering BOM is matured, so it's been production released. That's the usual status or a next level milestone in any product development happens. So once the product is released, a particular engineering BOM is released, as a complete product is matured, the expected changes will be very minimal. This is right time to build a physical twin. So here I am just showing a physical twin of a washer. That image, just consider like it got more sensors where we wanted to track or observe the performances. So yeah, that's a physical twin, and all information communicated from the physical twin into the virtual world is referred as digital shadow. Basically, let's see the and again, like the physical twin and digital twin must be identical. This is when we'll have a full benefit realized. Let's see the primary data sources. So physical twin data. So this includes all the data necessary for a specific purpose. All information communicated from the physical twin into the virtual world is referred as physical twin data or a digital shadow. It's called the other name. And for example, it is categorized into two ways. Like one is structured data, since like we are taking the information from a sensor. We know already like what we're going to monitor. So if we know already what variables we are going to get, that's a structured data. For example, if I'm pre-processed sensor data, if I'm monitoring for let's take this as an example. So the washer lid, always when it's getting closed, at what force it's getting closed, that particular information I wanted to track, that's a structured data. There are some unstructured data. Usually it's sounds or images. It cannot be really processed immediately, and what kind of information we will be taking it out. Those are unstructured data. And then additionally there is supplemental data. meaning this data we have to always feed into the system ourselves, like it is not coming from the sensors or anything from the physical twin. It is some based on the sensors where we have kept those informations we have to feed. So those are all supplemental data. For example, the location of a sensor. um, um, in this way, anomalous behavior can be precisely identified by the geometric location of its origin. So that's a key source of supplemental data. And then the self. So once we have this information is being transferred from physical twin to the digital twin core, we will have a self evaluation. Basically, the it describes the property, not only the digital twin changes throughout its life, but also that it can be undertaken autonomously. This is guaranteed by the capability of the bidirectional data exchange. Um, this is the one. And the when we say the analysis and interpretation of the data sent from the physical twin are enabled by the context formed from the digital model, the digital twin and the digital thread. Now we move from the product development and build. So this is happening. Okay, and now we move from the product development to the build phase as maintained. This is when like it's getting hand over to the customer. The product is getting hand over to the customer as maintained status. When the product get into customer, it is in use. It is in use. So we'll get all the in use data in the form of physical twin data. It's going to be continuously streaming. That is an expected one. And to predict and optimize, whereas in the build phase it was on demand. Actually, when we were doing here, it was on demand. On a selective use cases, we know like where to test, but when it is in the use, we can expect multiple use cases, unexpected results we'll be having. So that's an advantage of in use, and we can learn from the data. Technically, actually, each model, each individual washer, like from the each home, is connected with the, one individual digital twin. I'm just showing every data connecting to a digital twin core for the sake of simplicity, but it is actually each will be connecting to an individual digital twin model. And yep, information derived from the analyzing a fleet, like there are a bunch of washers, fleets of digital can be changed to the digital model, basically with the learning whatever we are making, such as an adjustment of requirements based on actual customer usage profiles. It just affects that level. So this is the knowledge being generated. Even we could change the requirements according to the study what we have, analytics what we have made. So that feedback data really helps improving the current and next generation of products. For example, I'll take washer lid lock switch, the whatever we have seen. So its trust level varies based on the humans. So how I am closing the door and how my son closing the door, or how my daughter closing the door, it varies because we as a human, we tend to close faster or tend to close gently. If really somebody is slamming the door, and of course that's getting damaged in a minute or based on the usage. So those informations will be shared into the IoT, and then like analytics is happening in the tool stack. And then if similar activity happens in the fleet, the entire and overusing. So again, that's a kind of an information we are giving it to the manufacturer, OEMs. Okay, this is really needs to be the property, material property has to be improved. So that is a one use case which I could think of from the in-use data. So the next one is generated data. It's also called as product customization data. A straightforward example, we can go with an example, is to extrapolate the remaining life of product based on the individual usage parameters. So in this one, the same washer lid switch example, I wanted to know what is the remaining lifetime it can, because since many times the door was locked by slamming, what is the remaining lifetime it can withstand. So those are all the generated data from the physical twin. Okay, and then the other is environmental data. So this is an existing one in any home environment indoor. Whenever I whatever sensors we are keeping, it's in the physical twin or in the real product. But if anything externally, I wanted to know okay, why the washer isn't running, if there is more temperature or very low temperature. So I wanted to know what is happening in the particular uh, indoor environment. Then the environment data really supports us, and it can pull the data from the thermostat, the particular homes, the environment, and know the external temperature or the indoor temperature, and with that we can conclude what is happening in the system. um, this helps to know the external elements basically. So that's it. The digital twin can be enriched or reduced depending on the requirements of the business model. So here whatever I have shown is very most of the data sources, but it can be increased or enriched as their share in today's products. There are much more digital twin being used with the focus on electronics and electricals and software. It's steadily increasing. The digital twin is the enabler for the rapid integration of new functions. Thank you.